dear students, in the last video I explained convergence of a sequence, definition when the sequence is said to be convergent, and also one theorem. If a sequence converges, then it converges to unique limit. And also this, if a sequence xn converges to a limit L, then for a natural number p there exists n and m, so that mod xn minus xm is less than epsilon for all nm greater than or equal to p. When do you say that sequence converges? Sequence xn is said to converge to a limit L if for epsilon greater than 0 there exists m, however large, positive integer, so that mod xn minus n is less than epsilon whenever for all n greater than or equal to m. Then we say that sequence xn converges to L. Understand this definition. Sequence xn is said to converge to L if for epsilon greater than 0 there exists a positive integer, however large, so that mod xn minus L is less than epsilon for all n greater than or equal to m. As I already explained, this is the definition. And what is the meaning of that? When to say that xn converges? Sequence xn is said to converge. Sequence means, you know that sequence means infinite sequence. We consider only infinite. If we consider the sequence in terms of range of the sequence, the terms of the sequence or range of the sequence is infinite. And sequence is said to converge to L if the infinite number of terms of the sequence lies in a small interval L minus epsilon, L plus epsilon. Infinite number of terms of the sequence are within this interval, then we say that sequence xn converges to L. And if a sequence xn converges to L, then we have this. There exists natural number p, so that for all nm greater than or equal to p, mod xn minus xm is less than epsilon. Now come to the theorem. What is that? Every convergent sequence is bounded. See, already I have explained all these things. You go through that videos and also notes. Every convergent sequence is bounded. I have proved this one. But converse is not true. What is the converse? Every bounded sequence may not converge. What is the theorem? Every convergent sequence is bounded. Very important. Convergent sequence is always bounded. Now every bounded sequence may not converge. To prove this, I take one example here. By taking example, I prove this. What is the example? Consider this sequence. To prove this, let xn is minus 1 raised to n, where n belongs to n. A sequence is defined by xn is a sequence defined by xn is minus 1 raised to n. You know that a sequence is defined in denoted by many different ways. One most convenient way is by writing its nth term. Nth term is given by xn is minus 1 raised to n. Now I prove that this sequence doesn't converge, but this is bounded. Why it is bounded? See, the terms of the sequence are minus 1 1, minus 1 1, minus 1 1, and so on. Sequence means it consists of infinite terms. What is the sequence? Minus 1 1, minus 1 1, minus 1 1. It is bounded. Why it is bounded? Because xn is greater than or equal to minus 1, less than or equal to 1. Range of the sequence lies between only minus 1 and 1. So it is bounded. Now, sequence is bounded, but it doesn't converge. We prove that it doesn't converge. Why it doesn't converge? To prove that it doesn't converge, let us take epsilon is equal to half. Epsilon is equal to half. Let p be any natural number, means positive integer, however large, however large, then 2p plus 1 is greater than 2p, which is greater than p. Correct? Therefore, now I consider mod of x 2p plus 1 minus x 2p, or x 2p minus x 2p plus 1. Consider mod of this. It is mod of, what is x 2p? P is any natural number. 2p is always even. What is minus 1 raised to 2p? 1. Minus x 2p plus 1 means minus 1 raised to odd. Minus 1. It is therefore 2. It is 2 which is greater than this epsilon. Epsilon is arbitrary here. We have chosen epsilon as half. This x 2p minus x 2p plus 1 is greater than epsilon. But if the sequence converges, then what should happen? If the sequence converges, then xn minus xm must be less than epsilon for all nm greater than or equal to p. If the sequence converges for a natural number p, however large, there exists n and m greater than or equal to p, so that mod xn minus xm must be less than epsilon. Now we have taken p as a natural number. We have chosen epsilon as half. But what happened here? For n and m greater than p, n and m are this. 2p plus 1, 2p are n and m. Greater than p, mod xn minus xm is not less than epsilon. Therefore, minus 1 raised to n, this sequence is not convergent. So what's your conclusion? Sequence is bounded, but it doesn't converge. Therefore, every bounded sequence may not converge. May not converge. So what is the theorem here? Every convergent sequence is bounded. Every convergent sequence is bounded, but converse is not true. We have proved by taking one example. Now I consider some more examples here based on definition. Examples based on definition. To prove that a sequence is convergent, I consider some examples. But see, always by using definition, it is not possible to test the convergence. To test the convergence, we have further different results. We consider mainly monotonic sequences. That is the next topic. Now I consider some problems, simple problems. By using definition, we have to test the convergence. Show that the sequence 1 upon n converges to 0. Converges to 0. For this you have to use definition here. Definition. First I consider mod 1 upon n minus 0, because we have to prove that it converges to 0. It is already given, prove that it converges to 0. Then what you have to do? We have to verify whether there exists epsilon greater than 0, so that for all n greater than or equal to m, mod 1 upon n minus 0 is less than that epsilon. If it is true, then it converges to 0. So I have taken 1 upon n minus 0. If it is less than epsilon, if 1 upon n minus 0 is less than epsilon, that is 1 upon n is less than epsilon, that is if n is greater than 1 upon epsilon. N is greater than 1 upon epsilon. Now we choose m as a natural number. Suppose n is a natural number immediately greater than 1 upon epsilon. Epsilon is however small it is. So suppose for instance, or for the sake of definiteness, take epsilon is 0.00001. Then 1 upon epsilon is however large positive integer. Suppose this 1 upon epsilon is, we choose m is a natural number greater than 1 upon epsilon, then what happens from this? Then mod 1 upon n minus 0 is less than epsilon for all n greater than or equal to m. All n greater than or equal to m. Therefore, 1 upon n converges to 0. This is the problem. Say, what is the problem? I explain once again. Prove that the sequence 1 upon converges to 0. 1 upon n converges to 0. Now, when do you say that 1 upon n converges to 0? For epsilon greater than 0, there exists a natural number m, however large, so that mod xn minus 0 means 1 upon n minus 0 is less than epsilon for all n greater than or equal to m. Now, here we have proved that there exists such m. There exists such m so that it may be however large, for all n greater than or equal to that m, mod xn minus m is xn minus l is 0 is less than epsilon. So xn converges to 0. For that, what we did is we have taken 1 upon n minus 0, xn minus l, it is less than 0, that is 1 upon n is less than 0. It is less than 0 if 1 upon n is less than 0, that is n is greater than 1 upon epsilon. Now, we have chosen m such a way that it is a natural number immediately greater than 1 upon epsilon. Then what happens? 1 upon n minus 0 is less than epsilon for all n greater than or equal to m. Hence, sequence xn is 1 upon n converges to 0. Sometimes 0 is called limit of the sequence 1 upon n. One more example, show that the sequence n plus 1 upon n n plus 1 upon n converges to 0. As in the previous example, consider mod n plus 1 upon n minus 0. It converges to not 0, it is 1, correct? It converges to 1. N plus 1 upon n minus 1, it is n plus 1 minus n upon n is therefore mod 1 upon n. As in the previous, it is less than epsilon if epsilon is greater than 1 upon n. Epsilon is greater than 1 upon n. Now, if less than epsilon, if epsilon is or n is greater than 1 upon epsilon, correct? 1 upon epsilon. Now here we choose m such that it is a natural number immediately greater than 1 upon epsilon. Then what happens? From this, mod n plus 1 upon n minus 1 is less than epsilon for all n greater than or equal to m. Therefore, the sequence converges. This sequence converges to 1. Now, these are the examples based on definition. Prove that sequence converges. We have used definition here. Now, definition, divergent sequence. When do you say that sequence converges? If mod xn minus l is less than epsilon for all n greater than or equal to m, there exists m for the choice of epsilon. And also you have seen in previous two examples, for the choice of epsilon there should exist m. Now, divergent sequence means, see, the definition is like this: a sequence Sn is said to diverge to infinity if diverge to first plus infinity if for the fixed positive integer k however large it is, k, positive integer k, there exists m belongs to n, so that Sn is greater than k for all n greater than or equal to m. See, the definition is like this: a sequence Sn is said to diverge to plus infinity if for k greater than 0, however large it is, there exists m belongs to n, so that Sn is greater than k for all n greater than or equal to m. See, that means the terms of the sequence goes on increasing here. If you choose however large positive integer, the term of the sequence is greater than that k. That is the meaning. Example is sequence 2n. What are the terms of the sequence 2n? 2, 4, 6, 8, 10, etc. 2n. Yes, etc. This diverges to plus infinity. Similarly, we define sequence diverges to minus infinity. When do you say that sequence diverges to minus infinity? This you follow now. Go through the definition again. It is easy. A sequence Sn is said to converge to plus infinity if Sn greater than k for all n greater than or equal to m. What is this k? Any fixed positive integer, however large. Similarly, a sequence Sn is said to diverge to minus infinity if there exists k less than 0, however small, such that Sn is less than k for all n greater than or equal to m. For all n greater than or equal to m. See, again I explain this. When the sequence Sn is said to diverge to minus infinity, a sequence Sn is said to diverge to minus infinity if for k less than 0, however small, there exists a natural number m, so that Sn is less than k for all n greater than or equal to m, less than this number. It is said to diverge to infinity, minus infinity. Now, definition of oscillatory sequences or oscillatory sequence. See, we have convergent sequence, divergent sequence, now oscillatory sequence. Oscillatory sequence means a sequence is said to be oscillatory if it is neither convergent nor divergent. So we have convergent sequences, divergent sequences. You know the definition. But some sequences, they neither converge nor diverge. They are said to be oscillate. And also a sequence, see we have taken sequence 1 upon n converges. Sequence 2n diverges. Now one more sequence that you have already taken, important sequence it is minus 1 raised to n. This doesn't diverge, correct? And this doesn't converge also. They doesn't converge and diverge. Such sequences are said to oscillate, and this is said to oscillate finitely. A sequence which is bounded and oscillates is said to be oscillate finitely. What do you mean by oscillatory sequence? It is neither convergent nor divergent, and additionally it is bounded. Then we say that it oscillates finitely. And a oscillatory sequence is said to oscillate infinitely if it is not bounded. See this sequence, minus 1 raised to n into n. I write the terms of the sequence here. It is minus 1 plus 2 minus 3 plus 4 minus 5 plus 6 minus 7 plus 6, so on. See here, because n is 1, you get minus 1, n is 2, you get plus 2, n is 3, minus 3, n is 4, plus 4, and so on. Now, it is neither bounded below nor bounded above this sequence, because minus 7, next minus 9, and plus 10, and so on. And it is oscillatory sequence. It is oscillatory sequence, and it is said to be oscillate infinitely. Why it is said to be oscillatory sequence? It doesn't converge or diverge. Neither converge nor diverge. In addition to that, it is not bounded. It is neither bounded above or below. Therefore, it is said to oscillate infinitely. See the definition. What I mean by oscillatory sequence? A sequence which is neither convergent nor divergent is said to be oscillatory. A oscillatory sequence is said to oscillate finitely if it is bounded. Oscillatory sequence is said to oscillate infinitely if it is not bounded. This is the definition. So you have studied what is convergent sequence, divergent sequence, what is oscillatory sequence. Next is monotonic sequence. Try to understand the concept one by one. I give the questions on this topic. What are the questions you may expect? Already the topic that I have covered, from that topic you can expect the question like this. Prove that the limit of a sequence, if it exists, is not unique. One theorem. Secondly, prove that every convergent sequence is bounded. That I have explained clearly. Every convergent sequence is bounded, but is a converse true? What is the converse? Converse is not true. For that I have taken example. Then definition. Define convergent sequence, define divergent sequence, define oscillatory sequence. These are the expected questions. Now, what is monotonic sequence? One more concept, monotonic sequence. Monotonic means there are two types, monotonically increasing, monotonically decreasing. A sequence is said to be monotonically increasing if xn plus 1 is greater than xn for all n, or xn plus 1 is greater than or equal to xn. Sometimes, say I have already told in the beginning, different notations may be used. I may use xn or sn or un, so on. Now in the notes I have used sn, so I use this. A sequence sn is said to be monotonically increasing if sn plus 1 is greater than or equal to sn for all n. What is the example? Monotonically increasing. 2, 2, 4, 4, 6, 6, so on. It is a sequence. And it is monotonically increasing because any term is greater than or equal to previous term. Follow the definition. Any term is greater than or equal to previous term. So it is monotonically increasing. And strictly monotonically increasing. Strictly monotonically increasing. Strictly monotonically increasing. If Sn plus 1 is greater than Sn for all n, we say that it is strictly monotonically increasing. It is monotonically increasing. It is strictly monotonically increasing. What is the example? This is the example. 1, 2, 3, etc. n and so on. Sn is equal to n. It is strictly monotonically increasing. Monotonically increasing. And it is monotonically increasing. Similarly, we define monotonically decreasing. What do you mean by monotonically decreasing? Sn plus 1 is less than or equal to Sn, then it is said to be monotonically decreasing. What is the example? 1, 1, 1 by 3, 1 by 3, 1 by 5, 1 by 5, and so on. It is monotonically decreasing. and strictly monotonically decreasing is Sn plus 1 is less than Sn for all n. Strictly monotonically decreasing. Understand, every definition is important. When you further proceed through this topic, all these definitions makes very important. Concept is important. Monotonically increasing, monotonically decreasing. It is strictly monotonically decreasing. What is the example? Example is 1, 1 by 2, 1 by 3, 1 by 4, etc. It is strictly monotonically decreasing. Now we have two important results on monotonic sequences. First is a monotonically increasing sequence which is bounded above converges to its least upper bound. A monotonically decreasing sequence which is bounded below, if it is bounded below, then only it converges to its greatest lower bound. Let me take that in the next period. First you go through this and try to understand the concept very clear. I continue these two theorems in the next period. Okay.